Hello, everyone. Thank you for coming today, joining AIAA Los Angeles section Saturday town hall meeting. We have a great event today. By the way, my name is Ken. I'm the events program chair. I just want to say a few logistics to you before I hand it to our section chair, Luis, um, for moderating and the introduction. So basically, we thank Longdale Library provide us this wonderful facility. Really appreciate, and please keep the room clean. We have a check-in table. Restroom is right outside, but you need to wave hand to the librarian so they can unlock the door for you. Um, so and you know we didn't bring a refreshment because they charge us a little bit more to clean the room. But after the event, you're welcome to join if you like. There's a cafe just across the street. Hamburg, fries. Please join us to continue if you like. Have fun and conversation. Thank you very much. I'm handing over to you, Luis. Luis is our section chair, so he's going to take over from here. Thank you very much. Thank you.
Thank you for the introduction, Ken. As Ken mentioned, I am the current section chair for the AIAA section. Today, I am very honored to introduce our two of our guests for our presentation. Um, and before I get started on that, just quick shout out to Ken. Ken, thank you so much for organizing this. You're amazing, amazing work as always. But yes, thank you, Ken. So today we have the pleasure of hosting the first place winner of our AIAA undergraduate individual aircraft design award for a particularly special blended wing body configuration. So first, I'll go ahead and introduce David. David is a David is a junior aerospace engineering student at USC and an AIAA member. David has already achieved remarkable milestones in his academic career. He's competed in two individual aircraft design competitions, earning second place in 2023 and first place in 2024, which is what we're going to be hearing today. At USC, he was an integral part of the design team, Design Build Fly. Design Build Fly, for those who don't know, is an annual competition hosted by AIAA every year for students to compete students from all around the world to compete. David served as the aerodynamic stability and control lead for the 2023-2024 season. Last summer, he gained valuable industry experience as a performance engineering intern at Regent Craft. And this year, he's going to lead an ambitious project. He's going to found the human-powered flight research team at USC with the goal of breaking the endurance world record. That's fantastic. So that was David's introduction. Sorry, I'll go ahead and introduce you, Dr. Jeffrey Spedding as well. So Dr. Jeffrey Spedding is a professor of aerospace and mechanical engineering at USC. He earned his PhD in 1981 from the University of Bristol in England, where he began his career as a research associate at USC the same year. His early work focused on models of insect wings and later expanded to modeling atmospheres and oceans. He became a full professor in 2005 and served as the chair of the Aerospace and Mechanical Engineering Department from 2010 to 2017. Since then, he has returned to his passion for teaching and research as a valued member of the faculty. So, with those brief introductions, I'd like to turn the attention over to David to go ahead and present. Thank you.
If I may steal just a couple of seconds of David's time.
Yes.
I met David as I teach a first year introductory class, Introduction to Aerospace Engineering at USC. And every year we have a handful of really bright students. And one of the characteristics of these really bright students is they just do what they have to do. And the paradox of teaching then is that they don't really need me. And so it's been with David here in this project. So I'm supervisor, that means I signed a couple of forms. But otherwise, everything that you're going to hear about is pure David. And hats off to him for that. And thanks for letting me be part of it. Over to you.
Thank you so much. Dr. Spedding is giving me way too much credit. The first class at USC that we have to take is Introduction to Aerospace Engineering. If it is true that all the work was me, it is also absolutely true that Dr. Spedding, it was your class that put me into this. I sort of actually joined aerospace engineering out of, USC was one of the few schools that I applied for aerospace. My other option was computer science at Georgia Tech. So, and your class was a wonderful introduction. Close. Yeah, thank you so much, Luis, for the very kind introduction. And thank you all so much for attending. The idea of the talk today is, as Ken and Luis mentioned, to talk about my design, but also a little bit of work that I've done since. So without further ado, I'll get started. And yeah, so I'll just start with a personal introduction, a little bit about myself. I am a junior in aerospace engineering at USC. I spent most of my time at USC in design teams. I was in the aero design team for a couple of years, and then this year I'm sort of doing a new exciting thing. We're starting the human-powered flight research team with a couple of friends. And as Luis mentioned, our goal is to beat the endurance world record of a human-powered airplane. So we have a couple of years to do it. We are running against the clock, but currently underway to build a quarter scale by the end of next semester. So that's very exciting. And also AIAA aircraft design competitions. I've participated in that since my freshman year. These are all of the airplanes that I've been involved in some capacity. Most notably, the two middle there are the AIAA entries. And also just a quick addendum, I just want to talk about this because this was my latest work and I was super excited about that. This airplane on the right here, you can see is a kind of an interesting configuration. So somebody actually reached out to myself and my colleagues at the Human Powered Flight Research Team. Does anybody here know of Red Bull Flugtag by any chance? It's a competition hosted by Red Bull where you build essentially a hang glider and toss it off a platform. It's mostly a showmanship competition, but a very interesting aero problem. And so I got to have a little bit of fun of this. So interesting configuration there. On the left is us testing a 2/7 scale model, and on the right it's the full scale thing. Unfortunately, we had a bit of a structural failure, so the flight was quite majestic. Still glided around 40 feet, but a very, very fun experience overall. And up next, human-powered aircraft. That's what I'll probably be busy with for the next couple of years at USC. So let's get into the topic of today. The talk is kind of split into three parts. So I'll first give an introduction to the motivation behind this, which is solar radiation management. Then I'll talk about my design. I'll try to fly through that pretty quickly because at the end I have some exciting work that I've been doing, specifically a piece of code that I've written for performance analysis that gave me some results, but there's a lot of next steps there. So I'll talk a little bit about that. But yeah, so let's get started. So in 1997, two scientists published a very important paper that essentially summarized and looked into quantitatively where energy is absorbed and reflected into and out of the Earth and within it. This diagram became known as the Trenberth diagram, and it's essentially a summary of in units of watts per square meter where energy stays or leaves the atmosphere. And in the topic of climate change, with temperatures rising around 0.2 degrees Celsius per year, this is really important if we want to understand how we can mitigate the effects of this. So there's a couple of options. The option number one, which is what is used most and what has been most studied and is implemented the most currently, is to address this right side of the diagram. So reduce how much heat we are keeping in the atmosphere by absorbing it, mostly due to greenhouse gases. A couple of interesting papers that I've read and some interesting findings is it's been pretty well shown that it's technically feasible to halt the increase to achieve greenhouse stabilization. Although a lot of these models assume pretty optimistic use of carbon sequestration methods and even some economic and legal ways. For example, the European Union emissions trading system, which is far into the program. And another interesting thing I found is a lot of people are also warning of this term called mitigation deterrence, which is putting too much optimism into carbon sequestration instead of just reducing carbon emissions in the first place. Another interesting thing that I actually learned from Dr. Bradley's class, so there's already people doing this in the context of aerospace. There's a startup that sends balloons, which is with essentially a fridge. They claim they're taking advantage of more efficient sequestration methods in the lower temperatures. of the high troposphere, and even claim that there's a lot of cost benefits. So there's definitely potential for aerospace to jump on the right side of the diagram. However, what this competition was about is the left half of the diagram. Another option is, instead of decreasing the amount of carbon that we keep in the atmosphere, is to increase the amount of heat that we reflect, a lot of it from clouds in the higher stratosphere. A lot of the motivation behind this came from studying periods after volcanic eruptions. There was a major eruption in 1991 that was very well studied, and a lot of things that were observed is reduced, most notably reduced temperature around the eruption because of the release of sulfur into the atmosphere. And there's been a lot of research into investigating the artificial release of sulfur and as an analogous to natural phenomena. But the truth is, there's still a lot of unknowns and a lot of potential negatives with this approach, including but not limited to ozone damage. There was a big campaign against CFCs and the concept of ozone damage, and a lot of other potential negatives. So a lot of questions to be still answered there with the research. But just another interesting example of just how early we are in this process is there's some people already doing it. So we are early enough in studying SAI and artificially injecting aerosols into the atmosphere that there's not a lot of regulation against it. And instead, there's this company that has already released hundreds of balloons filled with sulfur dioxide. They're criticized by many. Others say that they're moving fast and that's what we need to do to save the Earth. So the truth is, there's a lot of research to be done in that area still. So a little bit more about stratospheric aerosol injection, which is where aerospace would jump on this, the idea that we can artificially release aerosol into the atmosphere to reduce or halt the increase in temperature of the Earth. A few questions that come to mind naturally is, should we even do this in terms of aerospace? Should aerospace even do this? Does it make economic sense for us to do this? And interestingly enough, there was this paper in 2012 by researchers from Aurora, Harvard, and CMU, very smart people, that deemed that yes, but not only yes, very interestingly, that a new aircraft design would be most economically feasible to deploy the amount of payload that we would need to deploy at the higher stratospheric altitudes. There was a lot of uncertainty surrounding engine design, and I'll touch on this a little bit later, but very interesting finding from this paper. The other question that's sort of paired with that is, how much aerosol would we need? There's a bit of disagreement. The general understanding between that one joint study and then some further studies from Yale is that around 1 megaton per year, between 1 and 5, to halt 1 watts per square meter, and on the upper closer to 5 would be enough to offset around 50 years of increase in radiative forcing in watts per square meter. However, there's also some other researchers that claim that even in the beginning of a potential program to develop airplanes that release StratoSOL, we could still have significant progress. So there's one paper that assumes 0.1, so around a tenth of what this competition, for example, was inspired by, and that would still have significant effects, almost halving the temperature change. And then from there, as we build more aircraft, to ramp that up linearly. So in the topic of this competition, the request for proposal for the 2024 competition used numbers from a conceptual design by Yale researchers that I'll talk about in a little bit. They assumed a fleet size around 180 to 220 airplanes, so that's quite a lot of airplanes, flying 3 sorties per day that would require a single airplane to fly 30,000 pounds of payload to 65,000 feet. So that's a lot of payload to a very high altitude, and it's hard to find a design nowadays that is able to do it. Hence the need or the question of whether we should design a new one. There's a lot of also interesting requirements here. So research indicates that it would be to have a more uniform dispersal of the aerosol. This would have to be deployed around plus or minus 15 of the equator. So these airplanes would also have to be able of deploying themselves. So we need ferry ranges of up to 3,000 nautical miles, which is another thing to keep in mind when designing something like this. So a little bit about the sort of baseline design for this competition, which was the SAIL-01 concept. So this was an airplane designed by some Yale researchers, capable of lofting 30,000 pounds to 65,000 feet, so the assumptions mentioned before. They went with a conventional configuration, Engine selection was a big question mark, but they ended up going with these F-118s, which I believe are the engines that power the U2, if I'm not mistaken. But the problem there is low Reynolds numbers effects at super high altitudes brings a fear of compressor stall. So you would have to have engines that are designed specifically for that purpose, or at least capable of flying that high. A little bit more of a 3-view diagram there. This is also from their paper. So interestingly, and I'll talk a little bit about this, but the payload density requirement is actually not terrible, and that's where one of the opportunities for something like a blended wing body would come in. But yeah, conventional configuration, 6 engines mounted on the wings. It's also worth noting that they didn't assume any existing technology or any gain in technology by the entry into service, which I believe was 2035. So their idea was also to design something that can be built today. And that brings us into the competition. So this is a summary of the requirements. Also important to note that this is not leaning towards or against SAI. This is just answering the question that if it is determined by very smart people that SAI is safe and the thing that we should do, then what might an aircraft design for that look like? And the requirements for this competition in particular called for a flight crew of 4 and 30,000 pounds of payload into stratospheric altitudes, and also a ferry mission of 3,000 nautical miles, which will come in a little bit later. But with that, I started the design of StratoSOL. So I'll go through my design really quickly, and then talk a little bit about some analysis that I've done after the fact. But the main performance problem, the performance challenge of flying in the higher atmosphere is without doubt the density. So the density ratio, so the ratio of density at 65,000 feet compared to sea level is around 7%. So that hurts a lot. In aerodynamics, the lift you get is directly proportional to the density, so that's a direct hit there. But perhaps even as bad as a hit is in your thrust. So the lowest fidelity models for the amount of thrust that you lose at altitude tend to use around the square root of the density ratio. So that's a 25% hit in your thrust available at altitude. However, some other models, and this I used in my codes, which I'll talk a little bit about later, predict even worse outcomes. So these, I believe, are based off of engine decks, and it's described in J.D. Mattingly's propulsion textbook. These models assume something closer to a 5% ratio of available thrust at altitude versus at sea level. So that hurts quite a bit. Looking at similar designs, which is something that I also did at the paper, and that the Yale design does very well. Something to note about these airplanes is that there's a very high thrust mismatch, because you lose all of that thrust climbing to the upper atmosphere. You're left with really high thrust rate ratios at sea level. In fact, an airplane like the U2 has a thrust rate ratio of 0.6, which is around 2 times what a commercial airliner has. And in fact, if you watch a video of a U2 taking off, it's quite remarkable. It takes off in like 1,000 feet. So really cool thing to see, because it just has to carry all of that extra thrust to be able to fly at stratospheric altitudes. There's also a design question of speed, and this is intimately related to the coffin corner, which I'll talk a little bit about later. But the question is, you're fighting so much for a lift up there, so it makes sense that you would want to fly as fast as possible to reduce your lift coefficient, and hence need or alternatively need a lower wing area for the same lift at altitude. But it's not as simple as that. This is a big question to answer. So because getting a little bit more thrust available to overcome that drag is really expensive when you're losing so much thrust while climbing to 65,000 feet, and also compressible effects come into effect, which is something that is, as I found in my later study, pretty hard to model, and I'll also elaborate on this a little bit. So now a couple of notes on why a blended wing body might be a good idea here. So just identifying a few configuration opportunities that might raise that as a possibility. So first of all, and I mentioned this earlier, the payload density is not that bad. So you can see that in the Yale concept, for example, that they're their internal volume requirement just for the payload is not really severe. So you can imagine that a lot of that area of the fuselage would be really nice real estate to generate some extra lift. And in fact, the density assumed in the competition is around 15 pounds per gallon. So compared to the sheer wing area required to sustain flight at 65,000 feet, that is not a huge constraint in terms of configuration. There's also a lot of aeropropulsive opportunities from hybrid wings or blended wings, and this is just a very interesting quantitative argument for that. So this is in Raymer's design textbook. In there, he lays out basically a statistical study of maximum lift to drag ratios versus the ratio of wetted to reference area. So that ratio is just how much wetted area you're using to generate lift. And there's a very unimodal increase in maximum lift to drag as you use more of your wing area, as you use more of your wetted area to generate lift. And maximum lift to drag ratio is a very key design variable when you're flying at 65,000 feet because thrust is so expensive. So wing loading versus the thrust rate ratio, you're going to take a big hit in thrust rate ratio. So
what's the horizontal axis on the right chart?
Horizontal axis on the right chart is, that's cut off a little bit. It's the wetted aspect ratio, which is proportional to the reference over wetted area. So that's proportional to the ratio of reference of wing area to wetted area. Yeah, and then in Raymer's textbook, he uses that as a way to estimate maximum lift to drag ratio with some fitting constant for different types of airplane. But statistically, there is a trend with wetted to reference area and maximum lift to drag.
Can you define wetted area for me?
Yeah, absolutely. That's just the total the total area exposed to air on the airplane.
Okay.
So that includes fuselage, any protrusions, cowlings, and everything. Hence why a blended wing would have a lower ratio because most of its wetted area is being used as a wing. So yeah, so very interesting results from Raymer's book. Yeah, and so this is just a bit of a summary there. Covered most of these. There's also a lot of typical penalties of blended wings, or things that are generally used as arguments against blended wings are also diminished here. So you don't really have to pressurize a cabin because it's just a crew of 4, and also takeoff rotation, which is sometimes an issue, is basically irrelevant is a strong word, but you will see that some detailed or more detailed performance studies show that this can meet takeoff requirements of 8,000 feet with not a lot of problem because you just have so much excess thrust that you need to sustain flight at upper atmosphere. So yeah, so with that, I'll go through the sort of design process and then conclude with a little bit about some further analysis. So and this sort of follows the chronology also of the report itself. So I started by doing what's called a constraint analysis. So this is a plot of thrust rate ratio versus wing loading for a bunch of different performance metrics. This is one way to hone in on a design space for an airplane. So the idea is that every point on a line, and each line is one performance requirement, satisfies that performance requirement. And there's also an inequality, right? If you want to satisfy, for example, a climb constraint, any point that lies below that line doesn't satisfy the climb constraint. So that restricts your space also, not just a long line. And this is the result. So this is interesting. It puts you on a wing loading and a thrust rate ratio, but more qualitatively, it tells you what can be expected and makes sense, which is that that red and that blue line, which are well below the feasible design space, are basically inactive constraints. So rate of climb and takeoff are not pushing your design to a specific point because you just, again, need so much more thrust and so much more wing area to maintain flights at 65,000 feet compared to meeting the takeoff constraints. I also did what is basically the inverse of constraint analysis. So instead of picking a performance requirement and then varying thrust rate ratio and wing loading, you can do the opposite. So you can pick a thrust rate ratio wing loading, see what the resulting performance requirement for that is, and then vary thrust rate ratio and wing loading. So this generates what these are generally called carpet plots, So this gives some more insight into the design spaces. So also called like baseline trades, because you pick a baseline and then vary your design by a little bit and seeing how that changes. For sizing weights, and in general, aircraft design, you size for a weight, do the layout, analyze it, see if it meets the performance requirements. So for the weight sizing, I did what's well described in books like Raymer and Goodwinson. So essentially, you assume an emission profile, calculate fuel fractions segment by segment, and also for empty weight fractions is generally used a statistical data fit. So this is a power fit, so linear in log, and sort of converge on your weight like this. It is that you guess an initial takeoff weight, calculate the empty weight fraction, fuel fractions for that mission, calculate the takeoff weight again. If they match, you go with it. If they don't, you iterate until it converges to solution. After that, a little bit of layout. So I did it mostly in OpenVSP, if anyone's familiar. So that's a piece of NASA software that is very, very nice for layouts. There was a question here of the the configurations and the aero are very closely related because the airfoil selection here also dictates internal payload, and so I did some studies about that. There are some methods to estimate divergence, drag divergence Mach numbers. So that's one example there. That's also laid out in the report. That's Korn's relation. So you have that constant K is cataloged for a bunch of NASA supercritical airfoils. And here are some further for views. So further layout also in OpenVSP. So on the right diagram, it's missing a bunch of systems, but highlighted are fuel volume requirements and the internal aerosol tank. And you can see that even here, the internal volume requirement is pretty small compared to the rest of the internal volume. Difference being that center section is now also reference area, so it's more lifting than a conventional tube and wing fuselage. Also did some weight and balance analysis. In the down select, I opted to using those vertical surfaces at the end, similar to I had a picture of it on board, but if anyone's familiar with the X-48C, NASA did some studies with that and flight tested that configuration back in the, I want to say, early 2000s, possibly earlier. So did some weight and balance there. The idea of the vertical surfaces just gives you some leeway with static margin, just pushes your neutral point a little bit aft. So yeah, and also worth noting that there is, sorry to go back and forth, but there's good literature also on higher fidelity weight models for blended wing bodies, which is super interesting and also something that I use in the report. Concluded with some analysis, so aero, propulsion, S&C, and finally performance. So worked out some drag polars. On the right there is, I mentioned Mattingly's thrust model, which is a bit higher fidelity thrust model before. So that's that thrust model there on the right. Also did some stability and control analysis, and with some commercial software. So if anyone's familiar with things like Accelerator 5 and AVL, and also calculated some aerodynamic efficiencies and sort of spot checking at each stage of flight. And finally, performance analysis, which was a bit of a sigh of relief, though there is definitely more work to be done here, which I will show starting on the next section. But just some thumb plots, so flight profiles and flight envelope plots. And from these lower fidelity models showed that it would be able to maintain flight at 65,000 feet. So that's sort of a small rail line there, but the service ceiling estimated was around between 65 and 70,000 feet, so closer to like 67,000 feet for this specific geometry. And also, interestingly, and sort of as expected, takeoff, not a huge problem. So the requirements were 8,000 feet. This airplane would be able to take off closer to probably around 2,500 feet, just because it has so much excess thrust. So that concludes the design itself. So now I'm going to talk a little bit about some work that I did after. So I'm calling this StratoSOL Revisited. It's the sort of inspiration or idea for this is that those parametric trades that I mentioned early on good and they give some insight into the design space, but could do better. As I mentioned, also there's big questions here, such as how fast can you, and how fast should you cruise, and some other performance problems such as the engine problem. And so there's a lot of space here to do some higher fidelity work. And this is a highly interdisciplinary problem, as is a lot of aircraft design. And it just so happens myself and another colleague, Nicholas Nototsky, and a shout out to him for our flight mechanics class, we developed some time-based codes. And then over the following summer, a little bit before, a little bit during, a little bit after that summer, I took that code base and put it into a framework in Python with some nice object-oriented sort of framework, and so made it a lot pretty modular so that you can use a bunch of different models as you wish, and I'll talk about that a little bit now. So this is the sort of things that you can do with this code. So you will note that everything that I presented to you on the report was pretty analytical. So these were models that are essentially equations, but not a lot of simulation work. This allows you to do something a little bit higher fidelity. So what this code does is it essentially integrates the equations of motion of an airplane over time. And the nice thing about that is that you can keep track of whatever you want to keep track within the code. So on the left, the idea is that each point there is an airplane with a different wing area and a different aspect ratio that is simulated over the entire mission profile. And then I can extract a bunch of different states versus time. So I can look at lift versus time, drag versus time, power available, power required over time. And so I can, with a little bit more fidelity, narrow down the design space. So on the right there, you can see that is an example run for a single airplane of what these states over time look like. So after I simulate this particular airplane, I can extract each little point, which is a point where it was simulated, and it will have not only altitude at that point, but all of these other states that I mentioned. And a full trade study looks something like this. These are the sort of post-processing results they would look at, but you can extract even specific things from each airplane. For example, here I'm looking at propulsion energy versus time. So this is the amount of joules in your fuel versus time. So you can see that as it flies through the mission, it burns that weight, but each airplane that has a slightly different geometry will burn it differently, so the dynamics of the actual mission will change over time. And that can give you a little bit more fidelity when picking a design point. This is a little bit of a high level how the code is structured. So the idea is that you have a vehicle object, and this vehicle object has a bunch of different models in it, and the user can pick which models to use. That's what makes it modular and allows you to design a bunch of different airplanes. So it has a geometry model and a weight model. Examples of these, actually I'll give examples on the next slide, but if anyone's familiar with design literature, there's a bunch of different models in Raymer, Roscom, and Gudmundsson has a bunch of different models as well. And you can also choose different models that relate to the physics of it. So parasite drag, lift, and also propulsion, which is really handy. So some examples there of what I have implemented in code, most notably blended wing models, which allow me to do some analysis when it comes to this, but also bigger changes like different propulsion models. So I'm working on an electric and a hybrid electric in the works, so you can size and design a bunch of different airplanes with something like this. And a little bit more about how a mission is actually simulated. So the idea is that the user gives some inputs, so a baseline geometry, chooses which models to use. So is this a blended wing? Is this a conventional aircraft? What sort of propulsion will this use? And then designs a mission profile from a bunch of different segments. And so for this analysis, for example, I wrote a payload dispensing segment where not only you cruise, but you let out payload at a specific rate. And then you converge at the mission. The idea is that you are guessing something, simulating, and then checking if the convergence is valid. So essentially you're checking if the final energy is 0. If it's not, if you have extra fuel when you finish the mission, then you can fly with a little bit less fuel. So you reduce the amount of fuel and simulate it again. And then the end of it is a bunch of data, basically. So just for reference, like 400 airplanes turned out to be around 40 gigabytes of just numbers, of just things versus time, and also information about which models the user picked. And another note is I've set it up so that you can run this mission convergence scheme in two different ways. So one of them is mission fixed. So it's the example that I gave. So you fly through the entire mission. If you still have fuel left over, reduce the amount of fuel, fly it again. If you have a negative weight for the fuel, it means you didn't have enough fuel. So you sort of converge on a zero final energy by changing the fuel. But you can also run it in a different scheme, which is useful for ferry range studies, for example, which is that instead of varying the amount of fuel, you vary something about the trajectory. So you fly the entire mission with a fixed amount of fuel. If you still have fuel left over, it means you can fly a little bit further. So it iterates on a range of one segment, for example, which is what was used here to simulate the ferry ranges for these airplanes. I ran a bunch of a small validation study. If anyone's familiar with Stanford's SWAVE framework, this is a pretty well used design and sizing framework. So this is simulating a 737-800 with pretty low fidelity lift and drag models. And you can see that the mission profile ended up being pretty reasonable, and some of the energy related parameters gave pretty good results as well. So fuel burn and lift to drag ratios and some aero parameters were pretty close to SWAVE. And just for reference, this is an airplane that's flying 2,500 nautical miles. I found a line that 737 is going to hold between 162 and 190 passengers, and a takeoff weight around 175,000 pounds. So, which is actually turned out pretty close to StratoSOL. That was just by chance. So, what lessons did this code that works reasonably well tell us? Mostly, it just raised a bunch of questions. So, I'll just present you some interesting, a little bit funny sometimes results, but that might give some insight into this problem. Definitely elucidates the point of the coffin corner. So, number one, modeling can be pretty hard, and so this is a funny result. When you're flying at 65,000 feet and at Mach close to between 0.5 and 0.8 is what I was looking at. Some of the numerics can get tricky. So this is a compressible drag model that we learn in our flight mechanics class, and it works reasonably well for commercial transports. But when you start pushing it to these limits, it can break. And there's some indication that it might break. You can imagine that a computer might have a bit of trouble dealing with such large exponents. But that showed in the simulation results. So these are some simulations with an incompressible and then a compressible drag model. So on the left, incompressible, none of the wave drag corrections, and on the right, a compressible drag model. You can see there's a bit of trouble climbing there to 65,000 feet on the right. And if you investigate this further, which you can do because I'm outputting a bunch of states versus time, you will find that the drag coefficient is jumping to a whopping 50. For reference, this should be closer to generally count drag in terms of counts. So a count of drag is 10 to the minus 4. So that's a lot of orders of magnitude higher than it should be. And the reason for that is because that drag model is blowing up. So having a bit of trouble modeling these things, but something like what's done a lot also in performance and sizing is something closer to a surrogate model where, for example, you might take this representative geometry in OpenVSP and then sweep, and OpenVSP has pretty good models for wave drag, definitely much better than a CD of 50. And you can just basically sample drag coefficients around for example, variations of speed and angle of attack, and then interpolate between these results. So that's a good next step to investigate things like this. But let's assume for now that this is a really nice world and there's no wave drag, which is not a great assumption for Mach 0.8, but just for the purpose of looking at the performance of this thing. That still shows how important Mach number is. So on the right here, I have four airplanes. So this is the same geometry run for 4 different Mach cruise numbers. And the interesting result, you would think, is you increase the Mach number, your drag and energy requirements get terrible. But if you run the other way, that's not much better, and that's because of the coffin corner. So interestingly, the results for the lower end of the Mach range, so of 0.5 and 0.6, was having trouble climbing. And the reason was because it was hitting that left end of the coffin corner. So these are some further, these are some other states investigated over that. And so on the left, you have drag coefficient. On the right, you have throttle, which is really the ratio of of required thrust over available thrust. So if you have a throttle of higher than 1, that's no good. And the cruise starts in this segment here, just linearly ramping down. And you can see that, interestingly, as you decrease, so as you decrease and move up on this plot here, decreased Mach number gives a much higher drag coefficient during cruise, and that's because your induced drag is going way up after you're stalling. Same thing for the throttle. These airplanes at the lower Mach numbers cannot sustain flight at 65,000 feet, which is very interesting. And also, when I say stalling here, for the purpose of the code, the plane doesn't really stall; it just continues the mission. But if you analyze this in post-processing and see that the throttle is higher than 1, then that airplane cannot fly the mission. And so you sort of figure these things out in post-processing. And to conclude, a little bit of just a sort of a demonstration and a look into what a trait study for this airplane might look like, and if it gives some insight, and it certainly does. So these are 400 airplanes simulated, so this is more of a trait study, so varying the wing area and the aspect ratio, and then simulating this airplane over an entire mission. On the left there, you have the takeoff weight of the airplane, and on the right, the fuel fraction, so how much fuel compared to its takeoff fuel it needed to fly that mission. And you can see that, interestingly, there's a region there of not much lower, but lower aspect ratio than was selected. So StratoSOL and even airplanes like the U2 have an aspect ratio around 10. But you can see that this result is sort of pulling you towards lower aspect ratios. And we can investigate a couple of things. So one nice thing that you can do is plot what are called ISO lines, so lines of some constant parameter. Here are plotted ISO lines of constant ferry range. A bit hard to see, but all of these airplanes easily meet the ferry range requirement of 3,000 nautical miles. So this is 3,200 here, 3,400. So not a problem to fly the mission when you're all carrying fuel. But when you're climbing to 65,000 feet, thrust can be an issue. So these are ISO lines of cruise throttle required. So the amount of required thrust over available thrust at cruise. And so the idea is that a number above 100% would mean that your engines cannot output the thrust needed to overcome the drag. And interestingly, the only region where these ISO lines fall to under 100, so where you could fly at 65,000 feet, is found on this little corridor here, where the throttle required drops to under 100%. And so, in summary, what this sort of indicates that is, instead of the selection of 5,100 square feet and an aspect ratio of 10, as went with StratoSOL, might be worth looking at reducing your aspect ratio and perhaps flying a higher wing, because that will cost you in flying fast, but it will save you from falling off the left end of the coffin corner. And obviously, there's a lot more work to be done here. Actually, before I get into just another comment, also, you might wonder why is it such like a steep dip, right? Like, this is a fuel fraction of closer to 19%, and all of a sudden 16%-ish. The reason why is any airplane to the right of this is spending so much more time in cruise than airplanes in this region. So it's just burning fuel all throughout that plateaued section of the cruise segment, which is another interesting thing there. But obviously there's a lot more work to be done. So just a few next steps, and I sort of mentioned this a little bit earlier, but a refined compressible drag model would be nice. Something like a surrogate model would do wonders here. And it's something that these big design codes also do, fitting curves over surrogates of drag and lift and all of that. And with something like that, doing a refined trait study, and they say that optimization is just a very effective way of finding where models are terrible. And this is certainly the case in a lot of times when you're working with these sort of codes, and investigating that low aspect ratio corridor. And also I've brought up this big question about propulsion throughout this entire thing. And there's also higher fidelity propulsion models. Something like a proper engine deck would also be nice. But even these sorts of things give some insight into the design space. So yeah, that's about it for me. So let me just thank a lot of important people. So first of all, Ken, thank you so much for inviting me to do this. I really, really appreciate it. Yeah, I had a blast doing this project and was super happy when he reached out to invite me to talk. Thanks to Dr. Sakar Biahut. He's a professor at USC. He is advising me for the human-powered flight endeavor, and he also helped me a lot with this talk. Thanks, Dr. Marty Bradley. Dr. Bradley invited me to talk in his classroom as well, and I also sent me some of his material for geoengineering, and even during the lecture, I learned a lot, and really fun stuff, and so thank you. And last, but certainly not least, huge thanks to Dr. Spedding. Dr. Spedding advised me not only for this competition, but also for my first one, and it was an unequivocal and very quick yes every time I asked him, and I really appreciate that. Really appreciate for bothering you for an hour each week while I was working on this. And yeah, so thank you very much, and thank you very much everyone for attending. I'll leave my so I have like a website with portfolio and a bunch of contact info and my LinkedIn there as well if you want to connect. Yeah, and I'll also if anyone wants the slides, I'll definitely have it up on my website and my LinkedIn, but also candidly I distribute that. I have a bunch of references and cool things about design and StratoSOL there too. So yeah, thank you very much.
Luis?
Yeah, thank you for the presentation. Can we open it up to Q&A? I think I see a question in the chat from Kevin Burns.
We can turn on his microphone. Wait a second. Kevin, 1 second. Let's turn on his microphone. Kevin. Kevin, do you want to say something?
Yeah. I just wanted to ask if he'd considered distributed propulsion across the tail and wing for its advantages in fuel efficiency, enhanced lift to drag ratio, maneuverability by being able to separately control the vector thrust in the various engines.
Yeah, thanks for the question. That's a good question. I did not. Definitely worth looking into. So the way that these competitions are set up, they kind of give us an okay to look at a single configuration. Yeah. Oh yeah, yes, right. Yeah, so for the individual category, they essentially tell you pick something and design it all the way, versus a group project or a larger sort of design endeavor where you would split it into. I remember reading that I think some companies or some people do like red team, blue team, and then each one of them analyzes a whole configuration to its end. But that's an interesting idea, and certainly worth considering. I don't think anything's like that. I've never seen something like that for this flight regime, like 65K, Mach a lot. So yeah, I did not, but definitely interesting to look into.
Well, thank you. You gave a great presentation. If you're interested in the distributed propulsion, you can talk with Dr. Gohardani in Orange County. I think he's head of the local section down there.
Oh, okay, yeah. Thank you so much. I appreciate it.
He'd be happy to talk with you.
Thank you. That's awesome.
Question along these lines. That's
You need a microphone. They cannot hear you.
all right. Have you considered hydrogen-based like propulsion, like engines and that? I mean, in terms of propulsion efficiency, have you considered that? Why not? Yeah.
Yeah. Also not. It's an interesting question. I think like probably for something like this where you're like so close to the stall end, anything weight would be a big problem. So the first thing that comes to mind for hydrogen, I think it's the reason a lot of blended wing bodies look at hydrogen is the internal volume, right? Because hydrogen is so much energy density, but the volumetric density is a problem. And the ways to get better volumetric densities just come with weight because of compressing it to a lot of pressure or cryogenic or something like that. Yeah, another interesting study, doing a hybrid. I'm currently working on like a hybrid electric model for this. I think anything electric for this mission profile would be probably not work. But pure hydrogen may be another good thing to look into, because there's certainly the volume penalty might be reduced here, but just look at the weight and actually design the whole thing. So, yeah.
Mark, do you want to say something? Go ahead.
Sure. I do. Hi, David. I had to tune in very late, so I missed almost everything. And I'm on a phone. You can't see my face probably, but I used to work with Marty Bradley at Boeing, or we were in the same department at least. And I did go to his class and give a couple of lectures a week or so ago, it was following yours the week after yours. But so I hope to on the subject in general of geoengineering and SAI. So what I'd like to do, I think, is to maybe get Marty to send you a copy of the slides I showed, and see some of yours also. I think it's important what you're doing, and congratulations on getting the award and all that stuff. But you know, this is something and Marty had presented about a year and a half ago on the general subject of geoengineering with aerospace technologies, and we followed up a bit, kind of some creative thinking as well as more conventional, even though what you're doing isn't exactly conventional, but it's more conventional. Anyway, I hope to follow up, and I hope that Marty does share those with you as well. That's it.
Yeah, absolutely. Thank you. Yeah, thanks so much.
Yeah, this is Marty. I think there's a couple of opportunities to share some more material. Your report, I think, is that also going to be on the website?
Yes, and it's currently also in the AIAA website. Yeah.
Yeah. I also think that it would be worthwhile sharing the second and third place reports, which I have a copy of, which you can also get from the website. So can I give those to you? And I'll give those to you, Ken, and you guys can share those. You know, the way this played out is I put in the RFP and I never heard anything back. And the next thing I saw, David had won the competition, and it was like a year later. So I had no idea what, all the things that had happened. I was very excited to see that. And I think because it was an aircraft design focused competition, David had the best aircraft design work. But the other two reports were from Kansas, University of Kansas, and they focused more on the concept of operations, about what a cycle of flying the airplane would be and what the infrastructure required at the airport on the ground would be. So I think those are interesting. Their aircraft designs clearly were not the best, but I think taken together, it completes the system beyond the airplane. So I think that would be interesting. So I'll make sure that those two reports are also a little bit more available than generally. So anyways, it was a great surprise, and I really look forward to, although I'm a little bit challenged, you're going to be in my aircraft design class in another year. Is there anything left to teach him at that point? So we'll see how that goes. So I was very happy to see the result of the competition. So thank you.
Thanks so much. And thank you for the wonderful RFP too. This was super fun. And yeah, as Dr. Bradley said, I think it very much shows that my big interest isn't just the performance side of things. I just kind of went all in there. But yeah, a lot of the University of Kansas has really, they're actually historically like always have won the competition. Well, yeah, they're an institution where Jan Roscom used to teach, and so historically also. But yeah, they always have really good stuff on not only like ConOps and cost preparations, but also like considerations of previous aircraft and the business also sometimes side of things. So yeah, absolutely.
Luis, I think somebody, Om has a question.
Right. I can read it out for Om. So Om asks, what kind of aerodynamic control surfaces would control this vehicle as compared to conventional control surfaces?
Well, that's a good question. Not as exciting an answer because for my AVL, for my S&C work that I did, I just assumed conventional, couple of ailerons also sized with some methods in Raymer, and then some scripts that I wrote, and just a sort of, I guess they would be rudders and elevators. So rudder faders, I forget what they're called, but just the surfaces on the V-tails. I didn't look into anything other than that. Besides also, well, for all the drag models and performance calculations, I also assumed some spoilers. Those are all the surfaces that I sort of assumed or sized when writing the report.
Is that something you think you can add to the Aero Tool sim?
Ooh, good question. Yeah, I think so. And also, yeah, so for some insight, this might be sorry if this is boring, but the sort of way that I have it structured right now is that the same geometry model, so basically the same piece of code that you write to run the simulation is also used to generate an AVL input file. Also for context, AVL is MarkDrell is S&C software, so could probably have to do some a couple more nights coding, but yeah, I'm pretty sure you can add. Yeah, I would have to look into it. So, something to investigate, and more. And by the way, also, if there's something that analysis that lacks in this report, and that there's a lot of opportunity for further work, is S&C. I mean, S&C of blended wing bodies is pretty tricky. This is a little more conventional because it's got some tails in the back, but there's a lot more detailed work to be done there too as well.
Awesome. Another question popped in. This one's from L. Yeah. Sorry if you said this and I just missed this, but what caused the takeoff weight corridor in the AR, the
aspect ratio and linear aircraft?
Yes.
Yeah, that's a good question. So is it all right if I share my screen again super quick? Just to bring the plot up again. But this was over here. So the reason is, so as you it's because of the throttle required. So, and actually, sorry for moving the slides around quite a bit, but you can see that. So what it looks like, and this is also because of like how I set the code up. So you can see that this plane like clearly cannot climb to the plane on the right there. Actually, let me use the on-screen pointer so that people online can see as well. But you can see that when an airplane cannot climb, it doesn't just stop the mission. Instead, I have it set up so that the climb segment terminates after a fixed interval, so after 2 hours, at which point it just goes straight to the cruise segment. If it can't climb, it will be very clear that when it starts the cruise segment, it cannot maintain level flight by something like this. And the way that you verify that in post-processing is by doing those ISO lines of throttle. So if it's higher than 1, it can't fly, which is exactly what happens in that trait study. But also important to note is that if the airplane cannot climb to 65,000 feet, it will just stay in this climb segment here at, I don't forget the throttle setting that I use. I think is like, this is a pretty high thrust setting for all of the 2 hours that I set up as the termination, the limit for for the climb segment. So it's just burning so much fuel, even for basically fruitless work, because it's not going to be able to climb 65,000 feet. And so in the trait studies, this shows up. If you look at the results there, what happens is, and these are again isolines of throttle required. So up until the point where it is able to climb to 65,000 feet, it is just spending 2 hours in the climb segment. But as soon as it is able to climb to 65,000 feet, it will just spend the amount of time that it needs to climb to 65,000 feet, which is, here I was looking at, around an hour of climb time. And so there's a big drop there, because the airplanes that are slightly away from this corridor are not able to climb, so they'll just spend all of the 2 hours climbing. The airplanes in that little corridor are able to climb, so they finish their climb segments much quicker and therefore burn less fuel. So this is the reason for that is sort of because of intricacies of the code, but it is physical in the sense that that any airplane that is outside of that corridor is not being able to climb to 65,000 feet. So
I got a follow-up question on that.
Sorry. Yep.
It looks like you hit your altitude and then you're just slowly climbing because you're burning stuff. What about your payload? You got 30,000 pounds of aerosol you're going to dump, right?
Absolutely.
So as you dump that, would you get up there pretty quick?
Absolutely.
Your rate of dump.
Yeah, that is a very, very good point. Sorry. Yeah, so for everyone online, the question was, this airplane on the right, for example, it's climbing, but it has to drop the 30,000 pounds of payload, and so why does it not just start dropping it here? That's a very good question. So
it looks like it's climbing slowly because you're burning fuel.
Yes. Which you could just start dropping the payload at that altitude, right?
You got your mission altitude, go for it.
Exactly. So that's a good point, and that's a talk that I had with Dr. Biahut. Another good next step would be to instead have it set up so that this climb requirement has just brings it to the termination altitude. If your rate of climb drops below, say, 100 feet per minute, so if you've reached your service ceiling, just terminate and start dropping payload. That is certainly something that can be done. Here I just set up so that, if for some reason the requirement is a hard 65,000 feet, so if you're at 64,500, you can't drop the payload, and then in which case you would, just cancel the mission or something. That scenario would be kind of what is reflected here, but that's absolutely another thing that could be done, is to, instead of just running through that climb segment until I'm out of time, just check if my climb rate has dropped below a certain threshold, start the mission, drop the payload. So that's also something you looked at. Absolutely, what that would cause is it would sort of probably what it would do is it would splatter this sort of corridor into those lower throttle requirements, because those airplanes just wouldn't climb as high, but they would terminate as soon as they would terminate the climb as soon as they would reach that lower threshold ROC, and then start dropping payload. So it would just sort of scatter that region to the bottom right, that lower fuel fraction region. Yes, but very, very good point. And yeah.
Are there any models for turbulence? Because you can't climb as high if you have turbulence. Are you assuming your stratospheric, so no turbulence, or?
Yeah, no models.
Too chaotic to model?
Yeah, to be quite honest, do not know enough about that, about modeling turbulence, and there's the only sort of atmospheric modeling that's assumes is like just the thermodynamic, so pressure, temperature, density, following the standard atmosphere, U.S. standard atmosphere. Anything other than that, I do have working on it, but almost I think working headwind, so that would affect if you're tracking the 400 nautical miles in the ground versus in the air. So but no sort of turbulence, which is something to look at. Interesting. I have to do some research. Yeah.
I have a quick question.
Yeah.
Very quick question. So how many? So one payload is enough for one mission? You cover enough area, or you have to multiple payloads?
Yeah, good question. So the model that the Yale research assumes to get the enough payload per year is three sorties per day per aircraft, and a fleet size around 200 airplanes. So in order to reduce the 30,000 pound numbers, to reduce 50 years of radiative forcing in 1 year. So that's a large number of airplanes. The counter argument to that is that other paper, and there's actually a couple that argue this, that even a tenth of that could be enough to like half the temperature change. So if you have something closer to 10 airplanes flying 3 sorties per day, having the temperature change would be, with that weight of payload, would have the temperature change in 1 year. But the RFP for a single airplane, 30,000 pounds, would fly 3 sorties per day. So.
Yeah, in your paper report,
Yeah.
you say this going to be by 2031, right?
Oh, I believe so. Yeah, that's what
That's what you said.
Yeah.
So how many of those do you expect to be built to complete the mission?
That's a good question. I think the RFP assumes by 2031, and I also assumed this in the cost analysis that matched. Well, there's an asterisk there. So I believe I assumed 10 aircraft by 2031. Quite ambitious. But this is similar to the assumptions of the baseline project, and I think what's on the RFP. The reason, and I even feel bad saying that the cost estimates matched pretty well, it's because we used the same model. So both the Yale paper and my paper used the RAND's DAPCA 4 model, I think is what it's called. It's also laid out in Raymer. So saying that the cost estimates match is a bit of cheating because it's the same model that I'm using for a pretty similar takeoff weight. But there's definitely more work to be done in the logistics and cost estimate side of things. I believe the Aurora Flight Sciences paper that did cost estimation, theirs was more conceptual, like the feasibility. It was more of a feasibility study. I think they had a bit more personal. I think they talked to beliefs, so I don't quite remember, but there's definitely more work to be done on more specific cost estimation as well.
Are you up on the geophysical climate warming aspects or just the aerodynamic? Because what I'm wondering is, it's kind of a trade-off, right? You're increased carbon emissions, flying airplanes, burning fuel, and then you're putting atmosphere aerosols up there to increase your reflectivity. But has anybody really done a study to figure out is the payoff net positive because you're increasing carbon emissions while you're doing this? And if so, if you could do something with existing aircraft, additives to fuel or something, because there's no economic case for throwing up airplanes to, it's government expense to do something like that, right?
Absolutely. Yeah.
But if you could take existing aircraft with some kind of chemical formula that increases the contrails, then now you're talking about thousands of aircraft at lower altitudes, but you might accomplish the same objective if, in fact, it is net positive.
Yeah.
But that's not a critical question.
Yeah, that's a good point. I'm definitely just focused more on the aero things. I would hope just also for looks that if these airplanes fly, they would use like sustainable aviation fuel or something like that. It would look bad, I guess, if they were burning fuel. So the assumptions for the Yale paper, and I cannot quote the numbers of radiative forcing per amount of payload, but I would imagine it's higher than the fuel spent burning it, just because they're claiming like 50 years of radiative forcing for 200 aircraft flying at 3 sorties per day. But yeah, that's a good question. That's the policy side of this is as important as the aircraft design. And yeah, but I think the idea was that if this is feasible and this is possible, then what would an airplane look like? But definitely the if feasible and if possible, 1,000 different questions that are arguably more important or as important as the aircraft design itself, right? So yeah.
Can I comment on the last question also?
Yeah.
Is that okay? And it's not regarding your presentation, but it's more something that I had suggested to Marty and others, and to one of the guys probably was involved with the Yale project, was that there are a number of cargo flights that are polar, and the stratosphere is lower over the poles. So the cargo flights, there are, you know, a lot of them that come from China to the U.S. mainly, and they come with cargo and they go back mostly empty. So on the way back, one could inject aerosol on those flights, and so that's an idea how. And I think I got to, you know, like 2 million tons of payload if you were going to carry it all the way, but if you carry it only halfway, it might be twice that. And there were some other tricks to where you could get up to possibly even 10 million tons per year injected over the poles. And I think the poles are the northern poles, and I think that's the most critical area for climate change. So that whole logic is one way that you might start with existing fleets, just to follow up on that question.
It's more than just cargo too. When we were flying to China, those are polar routes.
Yes.
We stopped.
Yeah. Yes, but there was a huge mass that was, you know, that wasn't used. You know, a capacity that the aircraft had as they fly back. So you know, so that there was this, you know, they're flying back empty. So it's not too much more money to fly back with some payload that is dispersed in one way or another.
Yeah, obviously it's a different system you'd have to put on the aircraft to do that, but it's a good point.
Yeah.
I also noticed that there was a lot of empty volume in the aircraft, in your aircraft design. Maybe there's an opportunity there to make an economic case for payloads or, I don't know, passengers or anything like that to make some revenue.
Yeah, absolutely. Yeah, there's a lot of configuration work more on this as well. It should be done because I was that diagram didn't include systems, for example, but certainly looked like it, and then definitely something to look into. Yeah, and very interesting point about the polar routes. I recall reading that one of the concerns was damage to airplanes flying that route because they would be flying over a bath of sulfur, which is quite interesting. So.
Mm-hmm.
I have a question. Yeah. What was behind your selection of VTOLs, David? Can you provide me more context there?
Yeah, that was early in that just came from having a hard time getting a positive static margin. It was as simple as that. And you know, there's as I mentioned before, there's some leeway here in the individual competitions that you're kind of allowed to pick configuration and run. So my general process was, and for this and the previous year's airplanes, I basically have this spreadsheet set up with very low fidelity weights and everything. And so I'll just run through that and then lay it out in something like AVL or XPlayer 5, and then try to trim it and look at efficiencies and essentially pick the one that's that looks the best there. And I had a really hard time getting the weight and balance to work without the tails, but with those size tails, I pushed to essentially the static margin, the neutral point back enough that on those early down selects, I was able to get away with that. So, yeah. And also a bit of precedence as well. I was familiar with the X48C, and that's where AIAA should look at the configuration came from.
So you were saying that you mentioned something about silver. Would be the aerosol, we putting silver particle into aerosol. That's what you were saying.
Oh, sorry.
You mentioned something about silver.
It was sulfur. Sulfur.
Sorry, sulfur.
Oh yeah, I think that's the correct me if I'm wrong, it's the content of the payload, right?
Yeah, but that's also a good point. I mean, there are other aerosols, and one thing that I've suggested was that you might use aluminum oxide as an aerosol because it has some great properties that you know, and it doesn't harm the ozone. It has some other possibly some negatives, but aluminum oxide is a pretty good candidate. And if you skim through the charts that I showed to Marty's class, you'll be able to see what I'm talking about.
Awesome, sounds good. Yeah, definitely excited to look into that.
Yeah. And again, it looks like a small group here, but I just want to say that this is something that you know, it's something that when you do something in this field, you might save the world. You know, this is actually worth doing. It's way beyond earning money or things like that. This is you know, I think the world is in real crisis, and you know, for lots and lots of reasons, but one of them is climate change. So hopefully we might help.
Absolutely.
I wonder if I could ask a general question of the group of experts here. How high do you have to go for this process to work? Why do we have to go to 65,000 feet? How about 30? How about 25? What are the payoffs there? Did we just took that as a given, right? The 65,000
Yeah.
limit.
Yeah, for the competition was just a performance requirement.
Right. And that's because things stay for longer if they're up higher?
That's a good question. Yeah.
How much longer, and is it worth it?
So if you get above the triple positive stratosphere, then you're not going to get water particles and raining out.
Right.
I think is the theory.
But 65K is way above that, isn't it?
Yeah, so it varies. Like you said, it's lowest at the poles and it kind of swells at the equators.
Yeah.
But you could still be regular airliners that 737-800 you had up there. You can certainly get above the triple pos.
Yeah, that's right. Kind of routine. So
It's okay, and you know, summer, winter, that sort of thing.
Yeah.
But that's the real question. And if you could, in my mind, if there were some chemical solution additive to fuel that would still burn with existing engines, now you're talking. Now
yeah, that's right.
Yeah. Make it dent. But I was kind of surprised by the presentation because all I've seen so far are arguments about how the airline industry is contributing to global warming as opposed to potentially being able to help
it. I'll mention something else that you know, when you talk about airline industry, it looked like, and you know, this just occurred to me when I was preparing for Marty's lectures, but it looked like that if you disperse in and above the jet stream, that there's a natural convection type of you know, motion, atmospheric winds that will carry the aerosol upward. There's an uplift there, the way that the currents go on the Earth, so that there is a in the place that you would often want to go fly for, you know, for commercial flights to get that boost from the jet stream, then it may also be one of the best places to disperse aerosol. Just you know, kind of notional, but it was very interesting to observe that. And you know, I don't know how wide this distribution is. So I'm a little. I don't want to make everything public just yet. So I would say more.
one thing I'm not clear about is for the aerosol, is it supposed to reflect the solar radiation in and of itself, or is it supposed to like see clouds, well, cloud formation? I'm not clear about it.
Yeah, I would. I believe it's a mix of both. Yeah, I would refer to the experts for that, but the way this is a lot of times advertised is so for clouds. So I don't know. I'm not sure what the dynamics of the release and the reflection are.
So if you have to build 10 before 2031, when do you have to start to build it? Can you do it faster than Jet Zero?
That's a good, that's a good question.
Yeah, it's going to you first or they first?
Let's see. I believe I could build a 1% scale model in around 2 months. So I guess I'll need probably 100 of those to have a full scale. But in all seriousness, that's a good question. They don't have a requirement for like a manufacturing plan or anything like that. Imagine it wouldn't be anything too different from, for example, Jet Zero. So in terms of material selection, for this it was assumed like composite skins and like pretty conventional like aerospace structures for the weight models and everything. So.
Luis can tell you how fast they build.
Oh yeah.
Luis, are you going to be the first, or they are going to be the first?
We're hoping to be the first.
Everything is a big one.
Luis, did you hear that?
Sorry?
Professor.
We were wondering whether Jet Zero could make a donation.
That's above my pay grade, unfortunately. But no, honestly, awesome work, David. This is this gives me motivation. The work I'm doing at Jet Zero is we're all headed in the right direction, I think.
That's awesome. Thank you so much.
That's it. Okay. All right. Thank you.
Right. Yeah, of course. And I'll hang around for anyone in the room. I'll hang around here for a little while as well if you want to chat. But yeah, thank you so much for attending once again. I really, really appreciate it.
Thank you, David. Thank you, Dr. Spedding.
Luis, you want to say something about awards dinner?
Right. So as Ken alluded to earlier, I would like to invite both of you, David and Dr. Spedding, to our annual awards dinner, which happens early May every year. So in May, this coming May, we'd love to recognize both of you for your work and contributions to the section. Also, you're also invited to the student mini conference, which is, I know Ken mentioned already as well. It's going to take place February 21st. We'd love to, if you could even present, that'd be nice too. I know students across the 4 universities would love to hear what you're working on.
Yeah, no, absolutely. Thank you so much for the invitation. I'm happy to attend, and yeah, absolutely would be happy to talk. I love the work you guys do at the AIAA, so I'm really grateful for it.
Thank you. Well, I think that, Ken, that's it from my end.
Okay, all right. So let's conclude the event. All right.
Okay.
All right. Thank you everybody here and online.
Thank you, everyone.
Thank you, Luis and Professor Spedding and David. Thank you so much.
Thanks so much.